Hello, this video is for Stat 310, handout number 8, Part A, and includes a discussion of two-way ANOVA. Okay, let's go ahead and get started then. So the example that we're going to be looking at here has to do with out-of-seat behaviors. Okay, so we have children, and we're recording how many times they have out-of-seat behaviors during throughout the school day. This is a total over 5 days. So this individual here was out of seat 54 times over those 5 days. Now the two effects that I want to study here are going to be Ritalin dosage, and that is at 3 levels here: low, medium, and high. And then I also have 2 therapy programs that are being investigated, the behavioral and cognitive therapy program. So in this particular situation, or this two-way ANOVA, what that means is that I have 2 treatments, 2 things that I'm interested in studying: the Ritalin dosage and also the therapy program. Because there's 3 levels for dosage and 2 levels for the therapy program, I have a total of 6 buckets, or 6 different groups here. Okay, so those are being highlighted there. All right, so let's talk about the statistical model that is used to understand this data. It looks like this here. So this model is getting slightly bigger than the previous handout. The alphas, again, are going to be the effects due to the Ritalin dosages. So I'm going to have 3 alphas: an alpha for low, an alpha for medium, and an alpha for high. I also have some thetas in here, and that's going to be the effect due to the therapy program, the behavioral and the cognitive. And then I have one additional term in here that we have not seen before, and that's called an interaction effect, or a cross term. And that is the combination of the effect of Ritalin dosage and therapy program. Okay? So these might combine or work together to provide an optimal setting that may be different if you were to ignore that interaction effect. Okay, so we'll talk more about what we mean by that interaction effect down below here. All right. For this particular data, the mu term, or the overall effect here, is just going to be the average of everybody. Okay, so that's going to be 54.8. So if I took all of this data here and averaged all that data together, I would end up with 54.8. Now when we talk about the effect due to the Ritalin dosages, what we mean by that is we are going to put these people together because they both had Ritalin dosage low. So how much does the mean of these change because they're in this low group? That's going to be the effect due to low Ritalin dosage. So when I average these 10 values, I end up with a value of 53.5. Now, how much does that differ or change from my overall average? Negative 1.3. So this negative 1.3 here, what that represents is the effect due to low Ritalin dosage. I do the same for these and the same for these. Okay, so this, when I average here, that's going to be the effect due to medium. And then when I do high, that's going to be the effect due to high, which is a positive 1.2 here. So these sometimes are called marginal averages or marginal means because I'm obviously getting the margin of that table and computing the average. Now when I talk about the effect of the therapy program, what I'm going to do is average this way. So because all of these people were given behavior, or were in the behavioral treatment program, therapy program, we're going to average across. So the theta 1 is going to be the average of all of these, okay, subtracted from that grand average again of 54.8. So when I talk about the therapy program, we're going to compute the marginal means again, but I'm going to do that for the rows here. Now, it's not a coincidence that these things are opposites of one another. Okay. Because the design is balanced, that's going to happen. So the effect of the behavioral therapy program on average is negative 0.4. Okay. So a reduction in the number of out-of-seat behaviors from the overall average, whereas the cognitive has a slight increase in the number of out-of-seat behaviors. I should have said up above what we want to do is minimize these out-of-seat behaviors, right? So the goal here is to minimize these things as much as possible. Okay, so now let's talk about the last term here, which is the gammas, and that is going to be allow for the potential of the combination of these things. So maybe there's a particular combination that results in a better outcome. All right, so let's look at the gammas. When I'm talking about the effect, interaction effect for the low Ritalin dosage and behavioral therapy program, what I'm going to do is start with a 54.8. That's my grand average. Subtract off 1.3 because they're in, that was the effect due to low. Okay. I'm going to subtract off 0.4 because that's the effect due to behavioral. All right. This interaction effect just measures how much of a tweak or change is necessary because I'm in this combination. So here, that's going to be a positive 1.9. The 55 value is coming from just the average of these five here. Oops, I mean these five here, excuse me. Talking about gamma 1,1 here. Okay, so take the average of these, all right, and figure out what that effect is. All right, so that's the 55. All right, so I'm going to take 55 minus what this is, and I'm going to end up with 1.9 here, positive 1.9. Now, when I go to the low cognitive, the average is 52 here. So I'm going to use the same negative 1.3 here because this is low Ritalin. But now I'm in the cognitive therapy program, so I need to add 0.4. So this gamma 1,2 here is going to be the interaction effect due to this combination. All right, so that's negative 1.9. Negative 1.9 is what makes this equation equal 52. Now, I want to try to minimize the out-of-seat behaviors. So if they're in the low Ritalin dosage, it looks like I should have these kids be in the cognitive therapy program. However, when I'm in the high Ritalin dosage, it looks like I should have these kids be in the behavioral treatment program. So I want this number to be as small as possible, and 54 is obviously less than 58 here. So if they're over here on the right-hand side, I would like them to be in the behavioral therapy program because that average is smaller. But if they're in the low Ritalin dosage, I want them to be in the cognitive therapy program because this one's lower. So this particular model is going to have interaction present because I cannot universally say that the behavioral treatment program is better. It depends on, it depends on what combination or what bucket you're in here. Again, for low, I'd like to use cognitive therapy, but when I'm in the high, I would like to use behavioral therapy because that looks like it is minimizing the number of out-of-seat behaviors. In the medium Ritalin dosage doesn't really look like there's much effect there. So maybe in that situation, a kid could go either in a behavioral or cognitive there. All right, here's what a visualization is going to look like, for this particular data. All right, so the low, medium, high dosage levels, and then I got the two therapy programs being matched by here. So as I just said, we want to be as low as possible on the number of out-of-seat behaviors. So if I'm in the low Ritalin group, low dosage for Ritalin, I want to be in the cognitive therapy program. But if I'm in the high dosage level for Ritalin, it looks like it's advantageous to be in the behavioral treatment program. It's actually quite a jump here. I got a big difference there. which again, that's just the difference between the 54 and the 58 here. So for this particular, if you're in the high dosage level, it's advantageous to be in the behavioral treatment program. Okay, so now what we want to do is do a statistical test that's going to verify whether or not these gaps that I have, okay, are significantly different from 0. Because again, this red line is changing, right? This is just the view that I get for this particular data set, and this blue line has random variation in it as well. Okay, so let's go ahead and fit the model first. So let me bring the data in and fit the model for you. So I'm going to go Analyze, Fit Model. My response here is the number of out-of-seat behaviors. And then I got dosage is one of that's the Ritalin dosage. I got the therapy program. And then in order to get the gammas in there, I need to do an interaction or cross term. So I'm going to select both dosage and therapy and select cross. And that'll put that cross term in there for me, or my interaction term. Now I'm going to hit run. And as you might expect, I'm getting all sorts of output here. The output is quite long here, and it's also quite wide. Okay, so let's go ahead and start minimizing the output that I'm not going to be looking at. All right. Here's the analysis of variance. I got the parameter estimates, which those are just my different estimates here that we were talking about a moment ago. And then I have the tests down here underneath effect tests. So these are the p-values that I'm going to want to be concentrating on now. Over on the right-hand side, I got my multiple comparison stuff. Again, I'm going to have multiple comparison for Ritalin dosage. I could do multiple comparisons for a therapy program, or I could do multiple comparisons for dosage and therapy program. So I get all sorts of output here that we're now going to talk through here. Okay, the overall test, so underneath the analysis of variance, is just what that is testing is whether or not there's some effect due to any of these treatments or the combination of these treatments. So this test right here is not that meaningful in practice because it is not separating out each of the effects. So again, this is significant. So maybe let me start with the interpretation here. This is significant as less than 0.05, so that means I have some effect somewhere. Now, it could be due to the dosage of the Ritalin, it could be due to the therapy programs, or it could be due to the interaction term of dosage and therapy program. So that's not a very specific test. Now, what we do want to look at is the tests underneath effect tests. Now, I say here that this test should only be considered if the interaction term is not significant. All right, so let me go down and talk about the interaction first, and then I'll come back and tell you why this is not appropriate. So let's slide down in the notes here, and I'm going to do the interaction term first. So here I'm looking at the term, the p-value, that is associated with the dosage therapy program interaction term. And what this is going to do is just test all your gammas. Again, those are the interaction effects. Are they all equal to 0, or is at least one of those differ from 0? Okay. Now in words, what that is testing is the effect of the program does depend on dosage, or the null hypothesis is that it does not depend on dosage. Now, when we're looking at the graph again, we can see that the effect of the program, so what program is best? Okay, that's the question here. What program is best? Well, that depends on the dosage level. Again, if I'm in the low dosage, I want to use cognitive, but if I'm in the medium or high dosage, it looks like I want to use behavioral. So I cannot universally say that one therapy program is better than the other, nor can I say that one dosage level is better than the other. There's an interaction effect here. So this is significant. This is less than 0.05, which is telling me that I cannot isolate the dosage, the Ritalin dosage, and talk about that effect by itself. Nor can I isolate the effect of the therapy program and talk about its effect by itself, because these are working in combination with each other. Right? I can see that obviously in the graph. So it makes sense that this p-value is less than 0.05, because I can obviously see that what program is best or what dosage level is best depends on the other treatment. All right, so that's the idea of interaction. Now, what would it look like if this p-value right here was not significant? Like maybe it was like 0.2 or 0.3 or something. What if this p-value was not less than 0.05? Then you would say that the effect of the program does not depend on the dosage. And a graph that would represent that situation would look like this here, or what we would say is a parallel effect. So in this particular picture, the behavioral therapy program is best at low, medium, and high. So this graph right here suggests that there's not an interaction present, because the behavioral treatment program is best, regardless of what dosage level I'm on. All right. So if a kid is on low dosage, I'm going to want to select behavioral here. All right. So this is kind of the pattern that you would see when this p-value right here is large. Now, they don't have to be exactly parallel, but close to parallel. Now, that's not what I have with my data. I have this crossing here. I definitely have a crossing here. So this makes sense to me that this p-value is less than 0.05. Again, because of this, which one is optimal depends on what dosage level you're on. So if I'm in a parallel line situation, so let's suppose that I am in a parallel line situation, then you can go and look at the effects in isolation of each other. And that's what this p-value right here would do. So this 0.0173 is just going to compare the three different dosage levels against one another. It's not going to really worry about what therapy program they're in, so they're just going to average across the two therapy programs. All right, and likewise, the p-value here for therapy program is just going to average across the dosage levels. So if I just took all the blue dots, this one, and this one, and averaged that, and took all the red dots and averaged those, that would just be looking at the therapy program p-value. But again, in this particular situation here, we do not want to consider the 0.2361, nor do we want to consider the 0.0173, because I have a significant interaction. Okay, so let's put this all together here. In your model, okay, so if your model identifies a significant interaction, then the effect of each factor depends on the level of the other factor. In this case, you cannot talk about the main effects. So here, when we're looking at these, we want to start at the bottom and work our way up. So because the bottom has the interaction term in it. The bottom is the interaction term. So you should not, will not, okay, you'll go to statistical jail, I guess, if you start comparing the dosage levels in isolation of the therapy programs when there's interaction present, because that doesn't make sense to do. Likewise, you will not compare, shall not, will not, you'll go to statistical jail if you start comparing the therapy programs without worrying about what dosage level you're at, because they depend on each other. Okay, so when this term is significant, you do not look at these. Now, this affects our idea of how we're going to do our multiple comparisons as well. Okay, so I'm going to skip over the expanded estimates again. Let's get down to the multiple comparisons, which actually is going to be on Handout 8 Part B. So Handout 8 Part B is going to be where we look at the multiple comparisons for these. All right, that's all I got for this video. Have a good day. Bye-bye.